I think that it is time to talk about continuity. What does it mean for a function to be continuous at a point? For a function to be continuous in an interval? What does that really mean? Since your studies of pre-calculus, we have talked about continuity, but if you think about it, we were never able to give you a proper definition because a proper definition requires knowledge of calculus. It requires limits, and you didn't know anything about limits prior to taking this class. So the best that we were able to do back then was to tell you that a function is continuous if you can draw the function or if you can trace the function without ever having to lift your pencil. Because as soon as, let's say, you have to lift your pencil to continue tracing the graph, then that graph was not continuous. So continuity was really expressed like this, as a graph that has no holes, no jumps, nothing broken down in a sense, no breaks, nothing like that. So in other words, if I can trace through the entire graph without having to lift my pencil or my marker, then the function is continuous. And as soon as I reach, let's say, this point right here, and I have to hop all the way up to continue tracing the graph, then that graph was discontinuous at this value of x. Now, this was not a bad definition. It was not a formal definition of continuity, but it was not a bad definition. For the most part, it got us through most of our discussions, right? It was good enough. For example, see, I can apply it here. The whole idea of tracing the graph. If we look at this graph right here, is it continuous? Thinking about tracing the graph. So if I start, let's say, right here, and I trace along, I can continue forever tracing, and I don't ever have to lift my pencil. So therefore, yeah, this graph seems to be continuous by this informal definition that we have. If I look at the graph in the center here, again, from left to right, I start here and then I trace through the graph. And when I get here, the only way for me to continue tracing the graph is to jump all the way down. So then I can continue right here. I have to jump again and I continue tracing through the graph. Immediately, I know that this function is not continuous. And if I look at this one, from left to right, I go down, down, and then I get to this point right here, or to this region right here. And I'm going to have a bit of a jump to go to this point and then back up to continue tracing the graph. Well, it doesn't smell right. There's obviously something wrong. Even though it only happens with one point, there is something wrong. So this is not continuous. That means that based on that definition, this is a continuous function, but this is not continuous. The more efficient way of saying not continuous is to say discontinuous. Discontinuous means that a function is not continuous. And this one right here is also discontinuous. So, not a bad definition, even though it's not a formal definition. Now though, now that we are starting to get a grasp of limits, I think that we can do better. Now we can go ahead and state a more mature definition, a definition that is precise and that it uses calculus. So it is going to have the concept of a limit. And before I get there, why don't you pause the video and try to think about how that definition can be formulated, because it's really not that bad. Knowing that we're going to have to use limits is going to be quite intuitive. What does it mean for a function to be continuous at a point like x equals a? We're going to be focusing exactly around A and at A. So let me even put little brackets here to talk about a small neighborhood around A. This function seems to be continuous by our old definition, the informal one, the one that says if I start, let's say, from the left, I can trace through the entire graph and I never have to lift my pencil. So that seems to be pretty much indicating that this function is continuous. Continuous at every value of x in its domain. So this is the domain of the function. Let's say everywhere from here to here. The fact that I can trace through and I never have to leave my pencil is telling me that it is continuous at every single value of x, including a. So let's focus right now on a, and let's try to see what does it mean for a function to be continuous at a. I want you to look at the graph here on the left of a. On the left of a, the left-handed limit exists, is approaching f of a. On the right of a, the right-hand limit exists and is approaching f of a. And at a, the function is perfectly defined. When x is equal to a, the y value is f of a. It is defined, it lies on the function. There is a closed dot right here. So what this is telling us is that a function is continuous at a if the limit at a exists, the double-sided limit exists, and if the function is defined at a. Honestly, this is it. This is what continuity is telling us. It is telling us that the limit as x approaches a of f of x exists. But existing is not enough. What we want is for that limit to equal to f of a. And this is the value of the function f at x equals a. It has to be, f of a has to be on the curve itself. F of a cannot be somewhere here above the curve or below the curve. It has to be on the curve itself. So when we write this limit, the limit as x approaches a of f of x equals to f of a, there are three assumptions that we are making. Three assumptions. Number one, the limit as x approaches a of f of x must exist. That's what we're saying. This limit over here has to exist. Second, we are saying that f must be defined. It must be defined at x equals a. So f of a must exist. This is what we're saying here. F of a must exist. And third, we are saying that the limit as x approaches a, so that limit, and f of a, the value of the function at a, those two have to be equal to each other. So we want to make sure that the limit exists and that the function is defined at a, but that they're both identical to each other. Because we don't want something like this. Imagine the function going like that, an open circle right here. So in other words, the limit of this function beautifully exists, right? It is approaching some y value. Imagine something like this. It is approaching some number L. So the limit exists. But let's say that the value of the function at a is not where the open circle is located. So in other words, it's not at L. It is somewhere below L. Imagine somewhere there. Imagine that this is f of a. Well, if that happens all of a sudden, this particular function is not going to be continuous at a. If I trace along the graph, when I get here, I'm going to have to go down and then I'm going to have to go back. So I'm lifting my pencil twice to be able to continue tracing the graph. We want to make sure that this point is not floating somewhere here. It is exactly on the curve where it should really be. We really want this point to be right here, for example. So this equality is really telling us, is really making sure that not only the limit exists, but also the value of the limit is equal to the value of the function at a. We want to make sure that we can trace through the graph without ever having to lift our marker. So now that we have a better intuition about continuity of a function involving limits, let's go ahead now and state the formal definition. I always like to have the formal statement. I already started with the preliminary conditions. It says here, suppose that f is a function defined in a neighborhood around a. So we want to make sure, let's go here to the left. We want to make sure that around a, really close to a, our function is beautifully defined so that we can talk about the limit of the function at a. What are the y values approaching? What are they converging towards on the left of a and on the right of a? So we want to make sure that we have a graph around a. This is why it says that f should be a function that is defined in a neighborhood around a. So we will say that f is continuous at a if and only if the following is true. The limit as x approaches a of f of x has to be equal to f of a. That's what it says. And as we know, this is a double-sided limit. So then that means that the limit as x approaches a from the left of f of x has to be equal to the limit as x approaches a from the right of f of x. So those two limits, they have to exist and they have to be equal to each other. So this is what we're saying here. But that's not enough. We also want the function to be defined at a. In other words, f of a must exist, must be equal to a real number. And the most important condition, I need another arrow over here, is that all of these three must be equal to each other. Actually, what would be really nice is to put 3 arrows right here. We will say that the limit as x approaches a from the left of f of x must equal to the limit as x approaches a from the right of f of x must be equal to f of a. So when we combine this, you have the double-sided limit. The double-sided limit has to be equal to f of a. And all of this right here is captured here. The double-sided limit must be identical to the y value of the function at x equals a. Let's look at the title here, one-sided continuity. The continuity that we discussed just a while ago, it involved a two-sided continuity. The limit from the left had to be equal to the limit from the right of a. It had to be equal to f of a. So that was clearly a two-sided continuity. The thing is that sometimes we are not going to be that lucky. We are going to have a function f that exhibits continuity only on one side of a, not in both sides of a. That will happen. So these are the types of one-sided continuities that we're going to discuss. we will talk about right continuity, at, I'm going to use C instead of A, because if you notice right here on these graphs, we're talking about C. Same thing, variables. So C is going to play the role of A in our previous discussion. So that's going to be one type of one-sided continuity. And the other one is going to be left continuity at x equals C. So if a function is not continuous at C, it may have a right continuity situation or a left continuity situation at x equals C. So let's look at this graph on the top. Here is C. Let's focus right now on what happens on the left of C. So right here, we're going to be approaching C from the left. Just look at that. So when I look at the graph and I start approaching C from the left of C, the left-hand limit exists. That limit beautifully exists. It is actually equal to g of C. And I see a heavy dot at C. That means that g of C lies right on the graph. So I claim that this function is left continuous. And I can write the following. Left continuous at x equals C really means that the limit as x approaches C from the left of, here we were using g, so let me be consistent with that, of g of x is equal to g of C. That's what it means to be left continuous. Is it right continuous? Well, in this case, if I now focus on the right, let me use a different color here, on the right of C, and x starts approaching C from the right, so imagine x is moving towards C from the right, I'm going to try to analyze the right-hand limit. And when I traced through the graph nicely, I see that the graph has a limit right here. But unfortunately, even though the limit exists, the function is undefined at C. There is an open circle right here. So what I noticed is that the limit as x approaches C from the right of g of x exists is equal to L, but unfortunately, L, this number L, is not equal to g of C. L, if you notice, imagine that I position it here on the y-axis. L is somewhere there. Clearly, L is above g of C. So then, this function right here will not be right continuous at x equals C. So then, let's define continuity on the right. So, right continuous at x equals C means that the limit as x approaches C from the right of some function, I'm going to use f of x here, f of x should equal to f of C. It should equal to that. So practically then, these are the definitions that may be applicable to a function that is not fully continuous at a point C, but the function may have continuity on the left of C, or it may have continuity on the right of C. And the idea is the same, that the left-hand limit has to exist, but just existing is not enough. It has to be equal to the y value of the function at C. And right continuity means that the limit as x approaches C from the right exists. So the right-hand limit has to exist, but just existing is not enough. The limit has to equal to the value of the function at C. If we look at this graph right here, let's look at 1. The limit exists on the left of 1, so the left-hand limit exists. but I have an open circle. So this function is not left continuous at 1, and also it is not right continuous at 1. And there is a huge gap. See how that double-sided limit doesn't exist. So this function has completely no continuity at all at 1. At 2, same idea. The left-hand limit is different from the right-hand limit. So continuity at 2 is impossible. Now, does it have one-sided continuity? Well, on the left, the limit exists, but there is an open circle. So it is not left continuous. Is it right continuous? The limit exists on the right, but it is not equal to the function at 2. So again here, there is zero continuity. There is no double-sided continuity, and there is no one-sided continuity at all. So no continuity at 1, no continuity at 2. Anywhere else, though, is beautifully continuous. Between 1 and 2 is continuous. Between 0 and 1 is continuous. But at 1 and at 2, it exhibits no continuity, not even a one-sided continuity. Let's look at example 1. Example 1 is giving us a graph of a function, f of x. We can see it right here. And part A of the question is asking at which numbers is f discontinuous, and explain why. If you remember, discontinuous means not continuous, the opposite of continuity. So pretty much I see a lot of parts where the graph is very nicely smooth, so smooth here and here, but I see some critical values, some open circles and dots. That happens at 1, at 3, and at 5. So I'm going to be focusing on those values of x. Let's begin A. Remember the main definition of continuity. In order to have continuity at a point, right? So let's say at a point like x equals a, the limit as x approaches a of f of x has to exist, and it has to be equal to f of a. This is our big definition of continuity. And it's very important to keep it in mind. The limit has to exist at a, the double-sided limit. But that's not enough. That limit has to equal to the y value of the function at a. So let's use that. Let's keep that in mind in our analysis. Let us start with x equals 1. Is the function continuous or not at 1? Well, if I look at what happens on the left of 1 and on the right of 1, the one-sided limits exist, and they're equal to each other. So the double-sided limit, that means the limit as x approaches 1 of f of x nicely exists. It exists. But unfortunately, it doesn't equal to f of 1, right? If you notice, there is an open circle. That means that there is a hole. A hole means a break in the function. Something is not right. So because f of 1 doesn't exist, then we do not have continuity at 1. So we will have to say over here that f is discontinuous at x equals 1, unfortunately. So even though there is a limit, the function is undefined at 1, and that pretty much ruins everything. Now let's go to the other case, the other point. Do we have continuity at 3? If I now look at the graph on the left of 3 and on the right, I see that the graph is, it has a left-hand limit and it has a right-hand limit, but they are not the same. They are unequal. So I will say that the limit here as x approaches 3 from the left of f of x does not equal to the limit as x approaches 3 from the right of f of x. And what does that mean? That actually means that the double-sided limit does not exist. D and E doesn't exist. And if the limit doesn't exist, then the function is discontinuous. So then that implies that f, sadly, is discontinuous at x equals 3. Because for continuity, I have to have both. The limit has to exist and the function has to be defined at a, and they have to be equal to each other. All right, let's go to 5. There I see another critical part in my graph. So if I look at 5, I see that the one-sided limits, they exist and they're equal to each other. So that makes me happy. This is now telling me that the double-sided limit exists. The limit as x approaches 5 of f of x beautifully exists. But what is the bad thing about this? That now the value of the function exists, but it's not here. There is a gap, there is a hole at 5 because the value of the function is up here. So we're going to have to say, sadly, the limit exists, but it is not equal to f of 5. And if I don't have equality, then that means that f is discontinuous at x equals 5. Okay? So I practically have discontinuity at x equals 5, at x equals 3, and at x equals 1. Part B now is asking us to examine the type of one-sided continuity. Is the graph right continuous, left continuous at some of these points? And again, we have to focus on those critical values where we have dots and open circles. So let's start again with 1. Well, the limit on the left is equal to the limit on the right, great, but the function is undefined at x equals 1. So we are going to have to say there that that at x equals 1, we don't have one-sided continuity. So we don't have one-side continuity at all. Okay, nothing. All right. Now what happens at 3? I think that at 3, the function is left continuous because the limit as x approaches 3 from the left exists and the function is defined at 3 and is on the graph. So the limit is equal to f of 3. Fantastic. So at x equals 3 right here, we have left continuity. Left continuity. And why do we have left continuity? Because the limit as x approaches 3 from the left of f of x is equal to f of 3. So we have that beautiful equality. Now let's see what happens at 5. The limit, the double-sided limit exists there nicely from the left and from the right, but the function has a hole, it has a gap at 5, meaning that when I look up and I see this dot, the y value is not on the graph because of that hole. So the limit doesn't equal to the y value. So we don't have a one-side continuity at all. So we're going to say that, let me continue here, at x equals 5, again, we do not have a one-side continuity. We don't have it. So practically only at 3. Just at 3 we have the function is left continuous. I actually forgot to mention that the graph is not right continuous on the right of 3. I forgot about that. And this is why. Look at the limit, the right-handed limit. the right-hand limit exists beautifully, but the value of the function at 3 is not here, it's actually down here. There is a hole at 3 on this part of the graph. So therefore, while the right-hand limit exists, it is not equal to f of 3. F of 3 is not here, f of 3 is right here. So the function is not right continuous at 3. It is just left continuous at 3. I want us now to look at example 2. Show that the following functions are continuous and continuous for every value of x in its domain. So again, to show continuity, we have to show that the limit as x approaches a of our function f of x is always equal to f of a. This is what we need to be able to show. So when we do that, let's go ahead and try it out and see what happens. Let's take the limit as x approaches a of f of x. We know f of x. So in this step, I will replace f of x with the expression, so with the number c. F of x is equal to c, right? This is how the function was defined. F of x is equal to c. So then I go, okay, what is the limit as x goes to a of a constant function? This is already one of those limits that is in our toolbox, the toolbox that we developed in section 2.3. We know that this limit is equal to c. And what is c? C is exactly f of a, right? For any particular value of a can be 1, a can be 2, a can be negative 100. For any value of a, the y value is going to be c because the function is constant. Just going to do a picture, just going to show a picture, but I'm sure that a picture was not necessary. Here is my constant function, and you notice that a can be positioned here. This can be a, or a can be here on the left, anywhere. No matter what a is equal to, f of a is always equal to c. So then we conclude that this function, so therefore f of x, which is equal to c, is always continuous at any a. Doesn't matter what a is equal to, at any x equals a. And from now on, you can always make that assumption. Honestly, from now on, if you have a constant function, you know that a constant function is continuous everywhere in its domain. Now let's look at part B. F of x equals x to the n. N is a natural number. By the way, this fancy notation here is the symbol for natural numbers. And if you remember, the natural numbers are the counting numbers. 1, 2, 3, 4, 5, 6, all the way to infinity. So is this function, and you can imagine so many functions. You can have y equals x squared, y equals x to the third, y equals x to the 57, you name it. Are those functions continuous? And if they are, where are they continuous? So I know what I have to do. If I want to argue for continuity, I must show, somehow I have to show that the limit as x approaches a of f of x is going to be equal to f of a. And again, a is in the domain of my function f. That's what I know. So if I can show that this limit exists and that is equal to f of a, I can claim continuity. So then let's go ahead and begin with the limit. The limit as x approaches a of f of x, I'm going to go ahead in this step and I will substitute f of x with x to the n, just as I did before, right? F of x is equal to x to the n. And this limit right here is already in our toolbox from section 2.3. We already know that this limit is equal to a to the n, a to the n. But a to the n is exactly f of a. If I go and I take a and I replace it into the variable to calculate f of a, I get a to the n. So then, when I put this and this together, what is that telling me? This and this together is telling me that the limit as x approaches a of f of x is equal to f of a. Therefore, f is continuous at x equals a. So every time that you have functions, power functions like this, x to the n, you know that these functions are always continuous at every value in their domain. A can be any value in the domain of these functions. Now it's time to tackle the last part of continuity, the last type of continuity. So far, we have talked about continuity at a point x in the domain of the function. We were using a, sometimes we were using c. And these points were in the domain of f, and we ask questions, is the function continuous at a? Is the function right continuous, left continuous? But it was always continuity at a point. What about continuity in an interval? Why don't we start with continuity in a closed interval, AB? How do we determine whether a function is continuous in a closed interval, AB? So for a function to be continuous in a closed interval, AB, this has to be true. F must be continuous at every x in the open interval AB. So whenever you're given a closed interval, just like over here, so the closed interval from A to B, to talk about continuity in this closed interval, you first have to determine continuity in the open interval AB. In other words, is the function continuous in the interval from A to B, but without including the endpoints A and B? And the other condition is that f must be right continuous at x equals a, which means to be right continuous at a, that means that the limit as x approaches a from the right of f of x has to be equal to f of a. And hopefully that makes sense to you. Let's go back over here to the left, to the graph. We want to make sure that we have continuity everywhere between A and B. Because A is the left endpoint, there is no graph on the left of A. So we have to make sure that as we get close to A from the right, the function remains being continuous all the way through A, but from the right of A. So this is why right continuity is important to analyze as well. And then the third condition is that f must be left continuous at x equals, in this case, at x equals b. So now we have to go to the other endpoint, the right endpoint. As we approach b, we are approaching b from the left. So this is why we want to have now that the limit as x approaches b from the left of f of x should equal to f of b. So putting all three together, it says that every time that you have to analyze whether a function is continuous in a closed interval a, b, you have to make sure that f is continuous in all x between a, b, and also that f is right continuous at a, the left endpoint, and f is left continuous at b, and b is the right endpoint. If all three conditions are satisfied, then you now conclude. So you're going to say, if everything is satisfied, f is continuous in the closed interval AB. But all three conditions have to be satisfied. Imagine now that we have the interval that includes A, everything up to B, but not including B. So then that means that now we are dealing with this interval. A is included, B is not included. So how do you argue for continuity in an interval like this? The idea is pretty much the same as before. You want to make sure that f is continuous. I'm going to write cont, C-O-N-T, for continuous, just to save a little bit of time. F is continuous in the open interval AB. You want to make sure that f is right continuous at x equals a. In other words, the limit as x approaches a from the right of f of x is equal to f of a. And because b is not being included, then practically you're done. If you can show that these two conditions hold, then the function is continuous at this half-open interval. And finally, what happens if the situation is reversed? Now, f is undefined at A, but is beautifully defined at B. So the interval in question is the semi-open interval that doesn't include A. It includes everything else from A to B, including B. So in this case, you want to make sure that, again, f is continuous in the open interval AB, and you want to make sure that f is left continuous at x equals b. In other words, the limit as x approaches b from the left of f of x should be equal to f of b. In some of the later videos that will still be part of this section, we will apply these definitions in practical examples. I'll show you how to put them into practice to show whether a function is continuous in a closed interval or in a half-open interval. And briefly, the most obvious case, what happens if the endpoints are missing? Well, that's a super easy case. If this is the case, all that you need to do is to check that f is continuous at every x in the interval AB, but excluding A and B, just pretty much what happens inside. So just from here to here, at all of these values right here is what we want to be able to check. We ignore A, we ignore B. So we don't have to check for right continuity or left continuity, just continuity, double-sided continuity in the interval AB.